Welcome to today's webinar on how to maximize the value of failure analysis within the oil and gas industry, brought to you by Element Materials Technology. Before we get started, I'd like to cover a few housekeeping items. If you have any questions throughout the webinar, you may submit them on the right side of your screen, and we will address as many as possible during our Q&A session at the end of the webinar. If there are any questions we are unable to get to, we will follow up after the webinar. Today's presentation is being recorded. The link to the recording will be available on element.com and emailed to all registrants. After the webinar, there will be a short survey asking for your feedback. We would greatly appreciate you taking the time to share your thoughts. And finally, there have been reports of GoToWebinar freezing or losing audio going in the past. So if the webinar seems to freeze on you, our first recommendation for troubleshooting is to try refreshing your browser. Before moving on to today's webinar, very briefly, for those who don't yet know Element, we are one of the largest independent providers of materials and product testing services in the world. Element is the best and most trusted testing partner, providing high-value, critical services to the aerospace, transportation, energy, fire and building products, and connected technology sectors where failure is not an option. Our failure analysis experts are recognized as some of the most trusted in their field, providing reliable failure analysis for a variety of clients. Element has decades of experience performing failure analysis across many sectors. Our purpose is a simple one. We make certain that all of the materials, products, and devices we test, inspect, and certify are safe, fit for purpose, and compliant with all relevant industry standards and regulations. Together, we help our clients to develop better products, improve time to market, and help our customers become more efficient through the collective experience and knowledge of our team of over 6,000 engaged experts. Again, welcome everyone. My name is Lena Chernysheva, and I will be facilitating today's webinar. We are presenting to you from across the world today, from Singapore, the Middle East, and the United States. It is my pleasure to introduce you to our presenter today, Jeff Dodge. Jeff Dodge is the Failure Analysis Department Manager at Element Materials Technology in Houston, Texas. He is a graduate of the Colorado School of Mines and holds a Bachelor of Science in Metallurgical and Materials Engineering. He started his career as a failure analyst specializing in consumer packaging. In 2006, he joined Schlumberger, where he held various engineering and management roles focused on development of downhole tools and drill bits, which included laboratory and materials engineering management. During his time at Schlumberger, he earned 2 patents and a World Oil Award. Jeff is a certified project management professional and joined Element in 2019 to specialize in failure analysis in the oil and gas market. Dr. Basab Bhattacharya is the technical lead for failure analysis, fracture mechanics, and fatigue testing activities within Element laboratories in Middle East and Asia Pacific region. Dr. Basab is working across Element laboratories in Middle East and Asia Pacific, ensuring that these laboratories provide the necessary testing locally in accordance to the internationally recognized codes and standards. He is a well-recognized technical specialist with over 17 years of experience in that industry. He has obtained his PhD in materials science and engineering from McMaster University in Canada. He is a chartered engineer, chartered scientist, and professional member of IOM3 and TWI. Nabil Amir is an experienced failure analyst with over 7 years of experience in the field of metallurgical failure analysis, corrosion testing, and is a technical lead of metallurgy laboratory in Element, Saudi Arabia. Nabil holds a master's degree in material science and engineering from King Fahd University of Petroleum and Minerals in Saudi Arabia. Nabil has successfully completed API 571 corrosion and materials certification. He published and presented technical research papers in Middle East NACE corrosion conferences. Nabil has worked on multiple failure investigation projects and successfully managed metallurgical case studies from concept to completion on a variety of components used in oil and gas sector. And with that, I'll hand today's webinar over to Jeff.
Good morning, afternoon, and evening to all of you, and thank you for joining our webinar today. Here's a brief agenda of what will be covered in today's discussion. We've just completed a brief introduction to Element's global failure analysis capabilities, experts, and locations. We will discuss failure analysis and share with you some of our insights to help you maximize the value of failure analysis for you and your organization. Finally, we will share some case studies and have some time to submit questions and discuss next steps. I'd like to start with a few icebreaker questions. While some of you probably know the answers already, my intention is that by the end of the webinar, we will answer all of these for you. First, what does a failure analyst do? And how do they go about completing a failure analysis? The next question, who ultimately benefits from a failure analysis? Lots of options here. As the purpose of the webinar is to discuss value, what sort of value can a failure analysis bring? Maybe the value is monetary, in terms of cost savings from preventing the next failure, or maybe the value is in finding the new best practice for your organization. I'll let you think about this one as well. Following from the previous question, what is it worth to your organization to avoid the next failure? Or what is the value to improve a process or to determine a root cause of an issue? Okay, keep those questions in mind as we start the presentation with a quick definition. What is failure? Really, it is defined by the user and can be any non-conformance or unexpected result related to the performance or fitness for use. Typically, as we all know and have probably experienced, we know failure has occurred as soon as it happens. Failures in the oil and gas industry can affect all these different areas and components. Each specific tool, part, pipeline, or component can fail in their own specific way, given their own unique environment and application. Our experts across the globe have examined and determined the root cause of failures in all of these areas. The impact failure has can be seen in the annual cost of failure across the oil and gas industry. From catastrophic losses offshore to leaking or burst pipelines, the cost of failure is something we all understand and appreciate. As just one example, corrosion is a primary failure mechanism across the industry. As shown, NACE estimates nearly 3.1% of the US GDP and almost 2.5 trillion US dollars in worldwide losses due to the annual cost of corrosion. A proper failure analysis can help mitigate or eliminate future costs by accurately identifying the root cause of a failure, including, as we will see in upcoming case studies, those caused by corrosion. So corrective actions can be applied. Now that we have defined and discussed what a failure is, let's discuss the process of failure analysis. As you can see, the purpose of a failure analysis is to determine the root cause in order to eliminate similar failures in the future through corrective actions. How do we reach a root cause and answer all of the important questions surrounding a failure? By following a typical failure analysis process. The following is a very general overview of a typical failure analysis. Keep in mind that these investigations are often highly circular, which is why good communication between the customer and the failure analyst is so critical, as we will see and discuss in upcoming slides. The first step is gathering information related to the failure and the sample we are investigating. We must have a physical object to complete a failure analysis. Non-destructive testing is the first step in this, which always includes visual examination and photography but could also include radiography or other forms of NDE testing. Destructive testing, which requires cutting the part into smaller specimens for further examination and testing, is completed next. We use these sectioned pieces for mechanical and chemical testing and microscopic examination. We'll see how this works in the upcoming case studies. The last step is preparing and presenting the final report. This is the product that the failure analyst delivers to the customer. The report must support a root cause determination by effectively presenting the data and evidence collected during the investigation. Keep in mind that the root cause might be just a part of the information you receive from a failure analysis. Additional data, like how the failed component differs from other samples in the field or samples in inventory, could be highly valuable as an outcome to the analysis. We've mentioned a key player in the failure analysis process, so now let's introduce the failure analyst, that all-important person that does the work. What is the role of the failure analyst? It's pretty straightforward, but let's discuss a few items that the analyst is responsible for. First, collection and preservation of evidence, and examination of the fracture surfaces, which is a fundamental skill we will discuss on the next slide. The failure analyst directs the investigation and selects the relevant testing in order to complete it. Integrating all this photographic evidence and test data is a key responsibility. Failure analysts use knowledge of engineering, manufacturing, applications, material science, and other disciplines and combine them to find a root cause. The failure analyst will prepare a report which should be well formatted, clear, concise, and present the data a bit like a story, building on each piece until the root cause is described. Finally, the failure analyst is also a project manager and customer service provider. Communication with your analyst and from your analyst is required for a valuable failure analysis project to be completed. The primary skill that differentiates the failure analyst from other disciplines is expertise in fractography. Fractography is reading the fracture surface to determine the type of fracture that occurred. You can think of a fracture surface as a fingerprint that records the conditions at the time of the fracture, as you can see from some of the example images. The failure analyst always tries to find the location of the fracture origin and determine the direction it propagated. Without the fracture surface, we can't answer these fundamental questions, so preserve the fracture surface as much as possible whenever you experience a failure. The three smaller images you are looking at represent three forms of fracture. Failure analysts use the terms brittle and ductile as the first description of a fracture type. The fracture description, brittle or ductile, is generally independent from the actual material. For example, cleavage and intergranular fractures are both considered brittle forms of fracture, but occur frequently in high-strength oil-filled steels, which is generally considered a ductile material. Don't be alarmed if a failure analyst describes a brittle fracture in a material you know to have high ductility. And of course, if you ever have a question on any description used in a failure report you receive, make sure you have the failure analyst clarify it for you. To maximize the value of your failure analysis, you need to select the analyst with the right profile. You will want to partner with a failure analyst that specializes in oil and gas products, components, and specifications. Element offers a global network of dedicated oil and gas industry failure analysts. Many firms advertise failure analysis services, but determine if those experts are full-time or failure analysis is just one of their responsibilities. Just having lab equipment does not make one a failure analyst. It is a special skill set that takes development. Additionally, make sure the failure analyst has full access to laboratory resources. It's always a good idea to know how much testing the analyst needs to subcontract and how much they can complete in-house. You want an analyst with a minimum 4-year degree. Advanced degrees and certifications such as certified or professional engineer are also beneficial. Finally, look for someone you can build a long-term relationship with. You will get more value and faster turnaround by using the same analyst for all your failures. As you get to know the analyst and the analyst gets to know you, your products, and your reporting needs, you will capture additional value that would be lost if you work with a new analyst on every project. As we have focused on value, how do you, the customer, get the most value from a failure analysis? The answer is information. Share as much information as you can and don't withhold key information from your analyst. This usually ends up dragging out the project and ultimately costing the customer more in the end. Two-way communication is key, in the beginning of a failure analysis and throughout. If there is one key takeaway to maximize your value, it will be communication. what sort of things should be discussed. On the next 2 slides, we have specific examples of information that will assist with the failure. While we're all human and humans do have biases, the evidence will always lead to the root cause. It seems obvious, but you would be surprised how often the most important question is missed by the customer and more embarrassingly by the analyst. The question is, what do you want the analyst to determine? We may get a request to tell me why it cracked. As an analyst, I could look at the fracture surface and tell the client that it appears to be fatigue. That answers the question of why it cracked, but only sort of. Was the material in specification? Where did the cyclic stress come from that caused the fatigue? There's often additional data and investigation needed to complete a project, so a clear scope of work between the customer and the analyst is crucial for delivery of the project. We will want to know as much about the history of the part as we can. This can include original manufacturing data and material certifications. We will want to know what surprises were related to the failure. Note multiple occurrences of the same failure mode or other unusual observations. We always need to know the service conditions before failure. In pipeline failures, as an example, tell us what was flowing in the pipe, how long, what temperature, etc. The more information we have up front, the more targeted and efficient we can be delivering the project and the value faster. Please reflect on any recent changes related to the failure. Was there a new vendor for this component? Did you recently change material grade, etc.? Finally, sort of a fun one, but again, often missed, what was the component doing when it failed, and what was it supposed to be doing if there was a difference? Here are a few more examples that might be a little more challenging to discuss, but can be very important at the start of a project to save a lot of headache and wasted time at the end of a project. If you have received an in-house or third-party examination, share it in writing if you have it. Let the failure analyst look over the previous work and start to form their own opinions early in the project. Ultimately, it will save you time, as showing the analyst at the end of the project often leads to the need for discussions to reconcile the two opinions. Political and economic factors are important for the analyst to understand. As a failure analyst, my job is often to deliver bad news. As my client, I want to understand how I can best assist you in all aspects of the failure. If you're under pressure and need a rapid turnaround, let us know why. I'll better be able to support you if I know what is driving you. On the topic of rapid turnaround projects, to maximize your value, allow for some time for a proper investigation. Work on a mutually beneficial deadline that gets you the results you need and allows for the time to do a thorough analysis. It's often better to limit a rapid turnaround to key pieces of information early, like determination of the material properties, and then let the failure develop. That being said, if it's hot, and we'll do everything we can to deliver to your deadline. Finally, and this is really a big one, let us know if there is a chance the project could end up in litigation. Litigation has its own complexities and special requirements. And if we know that up front, we can make sure you have the proper expertise and experience for the project. If there was a safety incident, especially if there were injuries involved, please share that with us as well. At the end of the failure analysis process, what is the value you can expect as a customer? First, the failure analyst has an ethical duty to report the root cause without bias. Sometimes this means that the failure will be the customer's fault, but the value is in really knowing the root cause so you can create a corrective action that is proper and timely. This should eliminate or greatly decrease the chance of future failure. A properly communicated, completed, and documented failure analysis that reaches an indisputable root cause protects the customer from future damages. Finally, as we will see, the value you get from a failure analysis will be highly dependent on the level of partnership created between the customer and the failure analyst. A more efficient, meaning cost savings, and accurate failure brings additional upfront value by saving you costs. We'd like to share 2 failure analysis projects with you that highlight some of the topics we've just discussed. I'd like to point out that both case studies start with a report of a leak and initially show that corrosion may be a root cause. However, as you'll see, that as the investigations develop and the failure analysts follow the evidence, they have 2 very different root causes. I'll now turn the presentation over to Mr. Nabil Amir, who will present our first case study.
Thank you, Mr. Jeff, for a nice presentation. Welcome all. The title of case study, which I'm going to present today, is Corrosion of Stainless Steel Piping. The case study which is selected for this webinar is a very interesting case study regarding corrosion of stainless steel piping system, which has not seen service conditions. We have tried to keep the content simple so that case study remains interesting and can be understood easily. This failure investigation started with the collection of a background information and service history from customer, which is a usual way in all the failure investigations conducted by Element. This step of gathering information facilitates failure analysts to understand the events that had happened before and after the failure. Before going into the technical aspects of the case study, let me share the information shared by customer with Element. The information received from the customer revealed piping system to be corroded as various leakages were observed. The piping system was hydro tested for a period of 2 days. Potable water was used during the test. After the hydro test, piping system was dried. During the pre-commissioning stage of the project, exactly after 2 months of hydro testing, various leaks in the piping systems were detected at different locations. Material of construction was 304 stainless steel, which is a general purpose stainless steel with adequate corrosion resistance. After reviewing the background information, the objective of the case study was defined, which was to find the root cause of leakage in the piping system and to check if improper welding or manufacturing defects were playing any role in the leakage. Our investigation started with a visual examination of the pipe we received from the customer. The pipe was found to be fillet welded with a support plate and was painted on the outside. Leaks were observed at 2 different locations in the pipe at the fillet welds, highlighted with the blue circles. This was concern for our customer as the installation of the piping was completed and called into question if the welds were the cause of the leaks. At leak location, orange colored stains were observed. As leakage was found on the outside of the pipe, so we wanted to see the internal condition of the pipe, and that is the reason pipe was sectioned into 2 halves. The picture shows the inner views of the pipe, which revealed top half of the pipe to have a bright and shiny appearance, which is a sign of no stagnant water. The bottom half of the pipe was stained. This indicated that it may have been exposed to the hydro test water, which was not properly dried after the hydro test. Pits due to corrosion was observed on the inside surface at 2 different locations that corresponded to the areas where the pipe was fillet welded with the plate from the outside surface. As shown, the pits were hemispherical craters. The pits were found to be filled with corrosion product. Ring-shaped rust stains were observed around the pits, with deposits of reddish-brown corrosion product also observed. Similar type of pitting and corrosion deposits have been reported by different researchers in various stainless steel piping systems when the water in the pipe remained stagnant over a period of time. During visual examination, the leakage points were found, and in order to observe the cross-section of the leak locations, a metallurgical sample was cut from the pit for metallurgical assessment. Polishing and etching of the sample was carried out to differentiate between weld and base metal. The macro photograph shows cross-sectional views of the metallurgical sample, which revealed pitting in the weld. It was observed that the fillet weld, which was used to weld support plate to the pipe, fully penetrated the pipe thickness. No welding defects were found in the weld, like lack of fusion or cracking. The pitting initiated from the inside surface at the weld and can be seen in the micrograph. Appreciable metal loss due to pitting was observed at the pit mouth. The microstructure analysis revealed the phases present in the weld, which were found to be austenite dendrites and ferrite pools, which is a typical structure of austenitic welds. The ferrite pools in the fillet weld were preferentially attacked during the corrosion of the weld, leaving behind a skeleton of austenite dendrites. No interdendritic ditches were observed, which ruled out issues related to sensitization. Sensitization is a manufacturing defect in stainless steel, so this finding eliminated any questions related to the quality of piping used in this project. After conducting the microstructure analysis, high magnification scanning electron microscopy was also conducted on the metallurgical sample, which also revealed the selective phase attack, in which the ferrite phase was completely consumed, leaving behind a skeleton of austenite dendrites. Over the period of time, more ferrite phase was attacked, which leads to perforation in the weld and the observed leaks. EDS analysis, also known as energy dispersive X-ray spectroscopy, was used to determine the elemental contents of the corrosion product. EDS analysis of the weld area revealed the corrosion product to be comprised primarily of iron, chromium, and oxygen, indicating stainless steel corrosion products. Other stainless steel alloying elements of nickel and silicon were also detected. The carbon indicates organic deposits. Traces of sulfur and chlorine were also detected. EDS analysis found that the corrosion may have been influenced by the presence of iron oxidizing bacteria, as large amounts of iron oxides were detected. The presence of sulfur in the deposit may have been linked to the presence of SRB bacteria as well, which is known to cause pitting corrosion in steels. Based on the shape of the pits, the unusual selective phase attack, oxide deposit color, its distribution pattern, and EDS results, it was proven that the corrosion and subsequent leakages in the stainless steel pipe is caused by microbiologically influenced corrosion, also known as MIC. This failure mechanism is caused by microbes that attack the steel material, in this case, selectively attacking the ferrite in the welds. Mechanical and chemical properties of the weld and the base metal were thoroughly checked. Metallurgical assessment of the weld and base metal did not reveal any manufacturing or welding defects. Hence, welding was found to be satisfactory. The failure was caused by stagnant water that remained in the pipes after the hydrotesting. The rapid corrosion, just 2 months, is another strong indication of MIC. The bacteria that was present in the hydrotest water preferentially attached to the internal surface of the pipe, especially on the weld metal, due to more surface roughness and grain boundaries as compared to the base metal. Over the period of time, bacteria attack the metal and cause leakages. The value delivered to our customer was a clear determination of the root cause. This was not a failure caused by improper welding or manufacturing defects. By determining MIC, the customer was able to improve their future operations and respond to the failures properly. As shown, this failure was avoidable if the system had been thoroughly dried after hydrotesting. It's unlikely that MIC would initiate it, and without bacterial activity, the corrosion would not have occurred. That's it from the case study. I hope you have enjoyed the case study. Thank you very much. Now I would like to pass it over to Dr. Basab Bhattacharya, who will take you through another very interesting case study. Over to you, Dr. Basab.
Thank you, Nabil. It was a great presentation. Before I start my presentation, I must thank Lena for the nice introduction at the start of this webinar. Hello, everyone. The case study I'm going to present today is on a failed heat exchanger. The failure is really an interesting one. It's related to the sensitization of Incolloy 800H, which is a nickel chromium iron base alloy. Let us now briefly go through the background of this case study. Our client detected a leakage as well as fluid gas cross-contamination in a U-shaped heat exchanger after little more than 3,500 hours of operation. The heat exchanger was consisted of tubes and the shell which is covering this tube. Material used for the shell was 304 stainless steel and the Inconel 800H was used for the tube. As per client supplied information, The temperature of the superheated steam at the inlet, which is also called as hot side, supposed to be 500 degrees Celsius. The heat exchanger was operating at a pressure of 150 psi. Purpose of this study was to determine the root cause of this failure. The case study was conducted at our Singapore facility. As mentioned by our previous speaker, we have tried to keep the content as simple as we could so that the presentation remain interesting to all of our audience. Our client has delivered the heat exchanger to our facility for a detailed study, and after analyzing the background information and conducting visual information and examination, it was decided to do a hydro test in order to identify the location of failure. The location of leak was identified during hydro test and is indicated in the picture with a red arrow. After the hydro test, the shell of the heat exchanger was cut open and it was observed that one of the tube cracked at the hot side of the heat exchanger. It was also noted that the crack was very near to the stabilizing strap as shown in the picture. This particular crack tube in this presentation from now, it will be called the failed tube, was extracted along with few other non-failed tubes. These tubes were examined for establishing the root cause of this failure. As mentioned before, the material of the tube was Inconel 800H, which is an alloy used for high temperature application. Well, the first step was to do the visual examination of the tube surfaces of the failed tube, mainly a detailed observation of the failed tube, ID, OD, as well as the fracture surface was done with using stereo microscope. As seen from the micrograph of the fracture surface, it appears that the fracture surface is flat and perpendicular to the axis of the tube. Fracture surface appeared to be brittle. Additionally, corrosion observed on the fracture surface shown by white arrow. Corrosion also observed at the ID surface shown by white arrow. We have also seen wear on the failed tube, and it was evident as shown by the in the micrograph by the white arrow. The wear mark observed in the OD due to rubbing of the tube with the stabilizing strap. Vibration generated at high pressure caused this rubbing, and this also indicates the stabilizing strap must have been loosened during operation. Fracture surface observed under ACM microscope, in short ACM, both at low and high magnification. As Jeff mentioned, photography is very important examination for a failure analysis. And also it is worth mentioning that element laboratories are equipped with high-end equipment for detailed study. Scanning electron microscope, ACM, is one of them, and several locations of element laboratory has ACM facility. Fracture morphology observed under ACM presented in this slide. As shown in this slide, the fracture surface appeared to be flat and brittle in nature, as we've seen before. Parts of the fracture surface appear to be corroded. Corrosion product observed on the fracture surface even after extensive cleaning. Observation also showed transgranular fracture surface, and we also have seen secondary fracture crack. Some location of the fracture faces under high magnification showed intergranular fracture. So it can be concluded that the tube was going through a mixture of failure mode, which is transgranular and intergranular fracture mode. Detailed microstructural analysis done on this failed tube. Analysis was done both at hot side where there was crack observed, and also done at the cold side where there were no failure or crack observed. A detailed microstructural comparison was done for this two location and presented in this slide. Microstructure at the coal slide showed segregation bands of precipitate, as you can see in the photograph, micrograph. As per the supplied information, coal side temperature is supposed to be below 100 degrees centigrade. Therefore, it can be confirmed that this segregation band formed during the manufacturing process of the tube. Microstructure at the hot side showed heavy precipitation and they were even present in the grain boundaries. It was concluded after detailed study that segregation band, which was originally present in the microstructure before the application, before the operation, and at high temperature, they resulted in grain boundary segregation. Material appeared to be sensitized during operation temperature, operation condition of temperature and environment. Additionally, the microstructure at the crack location showed the crack appeared to be originated at ID, internal surface of the at the hot side of the tube. The crack morphology appeared to be both transgranular and intergranular type, which is a very typical feature of a stress corrosion crack. It can be established from above study that grain boundary segregation resulted in a sensitization of the tube at the hot side due to high temperature and environment condition. This sensitization led to the stress corrosion cracking (SSC) at the tube and adverse condition of operating condition. This finding also implies that operation condition of the heat exchanger was not properly monitored and the temperature might have risen beyond 500 degree, which is specified in the operating condition, specified operating condition of the heat exchanger. Microstructure analysis was also conducted on the non-filled tube in order to understand the issues with the filled tube. It was necessary to understand why only one tube failed among a bunch of tube which was there in the heat exchanger. Comparison made between failed and non-filled tube was done, and it was done for both the cold side and the hot side, and it's presented in the following slide. So now let us look at the micrograph once again for the failed tube at the cold side. Again, the segregation band was present. It was very dense, and we have seen even precipitation at the grain boundaries. The bands indicate improper annealing, whereas when we see the microstructure of a non-filled tube, the bands were almost not there and microstructure was almost clean. Similarly, the microstructure of the failed tube at the hot side showed heavy grain boundary precipitation. It was very clear that the failed tube was sensitized under adverse condition of the operating temperature and pressure. At high magnification, we have done an electron microscopic analysis of this precipitation, and what we see is we saw it confirmed there were precipitation. We have done chemical composition analysis using energy dispersive spectroscopy, which is in short called EDS, which is attached with our SEM. These EDS results are present in our next slide, but we will go back to the non-filled tube, which shows that very clean microstructure and there was no evidence of cracking and precipitation in this tube. This suggests that there is, due to some reason, the failed tube was subjected to improper manufacturing process. Most likely the tube was subjected to improper annealing temperature or cooling rate during its fabrication. The study also explained why other tubes didn't fail and only one tube failed and cracked during operation. As mentioned before, the EDS performed on the failed tube and during SEM study, and what we see is presence of chromium carbide at the grain boundary, which confirms very clearly the failed tube was sensitized. Presence of chlorine also observed in several locations, and one of the location was ID, and we also have done different analysis, and we have seen different non-filled tube also confirm presence of chlorine. Presence of chlorine may be originated from water used during operation, and that might have made the material prone to stress corrosion cracking. Stress corrosion cracking originated in the internal surface, resulted in the premature failure of the tube, one tube, but that's the tube. Yes, and the stress generated during operation accelerated the process. Due to adverse condition of environment, the sensitization happened at the temperature, even though it was below the 500 degrees centigrade. Sensitization followed by stress corrosion cracking, we can attribute to the unwanted microstructure of the failed tube, and that is also explained why other tube didn't fail and only one tube failed. Presence of chlorine during operation, most likely due to the uh, water which was used during the operation. So valuable takeaway from our client from this study was client would take right now more cautious approach for the manufacturing process of the heat exchanger, especially for the tube. They will advise their supplier to monitor the steps of fabrication of the tube. A better control will be implemented to monitor the operation condition of the heat exchanger. An element also advised client to use proper filter to ensure removal of chlorine from water. Well, this brings us to the end of our presentation. I sincerely appreciate your attention today. I would like to hand over to Lena and Jeff for the question and answer session. Thank you so much for your patience here.
Thank you, Jeff, Nabil, and Dr. Basab for sharing some interesting information on failure analysis and showcasing some informative case studies. We will now go over and answer some of the questions you have submitted. I will hand over now to Jeff, and he will pick some of your interesting questions relevant to his area of expertise. And Jeff will hand over to Nabil and Dr. Basab. Jeff, over to you, please.
Yes, thank you, Lena. And thank you, everybody, and thank you for your attendance today. We'll just go through a couple of quick questions here in respect to the time. The first question that came through, how long can I expect a failure analysis to take? Yeah, this is a good general question. Of course, it's going to depend greatly on the complexity of the failure, you know, the number of fracture surfaces that need to be examined, the number of samples that are involved. But generally, you can expect somewhere between 3 and 4 weeks for a general failure analysis. I think this is another key point where we can talk about the scope of work and why that discussion between the client and the failure analysis is so important. You know, the deadline and your time frame really needs to be part of that initial discussion so that both of you are on the same page when you're working on the project together. So thank you for that question. Very good and hopefully important to everyone listening. I will pass the presentation over to Mr. Nabil, and hopefully he'll have a couple questions related to his case studies that he can answer for all of you, and then he'll pass it over to Dr. Basab. Nabil, over to you.
Thank you, Jeff. I do receive some interesting questions submitted by the audience, and I have gone through the questions and selected 2 questions. Basically, these questions are related to the presence of ferrite content in the weld. The question asked is like, did you check the ferrite content in the weld? If yes, then which method was used and what was the percentage of ferrite count in the weld metal? Well, it's a very good question, as we have seen in the case study that the delta ferrite phase was attacked, which provides sites for a bacterial attack. So determination of ferrite content was necessary to see if it is exceeding the maximum limit allowed, which is around 5 to 6% in the weld. So yes, we have checked the ferrite number by using a ferritometer, and ferrite content was found to be in the range of 4 to 5. and it is not exceeding the maximum limits. There's one more question regarding the complete elimination of the ferrite content in the weld so that there will be no site for bacterial attack. Well, some of you may be aware that delta ferrite content is, intentionally introduced in austenitic welds to avoid hot cracking during welding. During the solidification of the weld, delta ferrite, does not allow solidifying liquid films of sulfur and phosphorus to form continuous network along the grain boundaries. As it is found that the presence of sulfur and phosphorus liquid films promote hot cracking in the austenitic stainless steel welds. As ferrite has more tendency to dissolve those sulfur and phosphorus as compared to austenite, and because of this important function, ferrite content cannot be eliminated in the austenitic welds to avoid providing sites for bacterial attack. Instead, we can avoid bacterial contact in the first place to save austenitic weld from MIC to happen. Now I would like Dr. Basab to answer some of the questions which he received during the presentation. Over to you, Dr. Basab.
Hi, thank you, Nabil. Yes, I did receive some of the question. Not in order, but I have a couple of things like did you do micro analysis from the at the fracture location of the failed tube? Have you seen any crack on the non-failed tube? Well, yes, we have done analysis on the failed at the fracture location, and we have seen ACC crack at the hot side, but there was no cracking observed in the cold side, and we have not seen any cracking on the non-failed tube, as I was mentioning. So hope that answered your question. The second question I have is, have you seen any secondary crack near the fracture area? Well, we have seen a secondary crack on the fracture surface, not on the micrograph, but yes, we have seen on the fracture surface a secondary crack, and these were mainly transgranular crack. And the third one, which is the last one, which I want to tell, which is the common one we have got it last time as well. Why annealing is important? Do you think annealing will help us to get rid of the carbide precipitation? Well, okay. When we do a forming of the tube, especially this tube which is made up of special alloy, nickel or corrosion resistance alloy or high temperature resistance alloy, it's very important that when we do formation, we do a proper annealing so that carbide precipitation doesn't form and it doesn't go to the grain boundary, because as soon as it goes to the grain boundary and we lose the effect of in a protective layer, it inhibits the formation of the protective layer. So it's very important. We can have a detailed discussion. If you guys want to have more discussion, you can send us an email, and you have the email at the end of the presentation. So yeah, answer to your question is yes, very important to have a proper annealing temperature annealing process. So I guess, Lena, due to the shortage of time, I will hand over to you for further question and answer session or whatever.
Thank you, Dr. Basab. We thank you all for participating in our global failure analysis webinar for the oil and gas industry. A recording of the presentation will be made available via a link that will be emailed to each of you in a couple of days' time. At Element, we make certain whether we complete a failure analysis for you or product testing, our global network of experts are here to assist you with the highest level of expertise. Should you have any questions or need to access our team of experts, please use any of the showing contacts. Thank you again for attending today's webinar. A short survey will pop up on a separate screen. And if you have a couple of minutes, we would really appreciate if you can fill this in. Your valuable feedback is very important to us. Thank you very much and have a good day.